Okay, let's try unpacking this little puzzle here. What is the next letter in the sequence? O, T, T, F, F, S, S, E.
Hmm. OTTFFSSE. Okay.
Seems pretty simple, maybe like a little brain teaser, right? But
Yeah.
think about the kind of mental gears you just turned to even start thinking about an answer.
Yeah, you're not just crunching numbers there.
Exactly. Today on the deep dive, we're not just focused on getting those answers. We're actually diving deep into the art and craft of how we find them, the process itself.
And what's really fascinating, I think, is that often the most valuable skill isn't just knowing formulas. It's about understanding how to approach something totally new, something unfamiliar.
Right. And that's exactly what our source material for today gets into.
Which is,
We're plunging into Paul Zeitz's brilliant book, The Art and Craft of Problem Solving. Now, this isn't your typical dry textbook.
no, definitely not.
It's aimed at those of you who enjoy math. Maybe you've even got some calculus, but you're probably more used to tackling what he calls exercises. You know, those questions where the method is kind of laid out for you.
Yeah, where you know which chapter section it came from.
Mm.
Zeitz makes this really crucial distinction, doesn't he?
He does. It's sort of like the difference between practicing, say, free throws versus playing in a real basketball game where anything can happen.
That's a good analogy. So in the book, an exercise, what does he say it is?
He describes it as something that tests your mastery of a specific technique, usually one you've just learned. It might be hard work, sure, lots of calculation maybe, but it's never really puzzling. You can generally see the path.
Okay, you know the steps,
Yeah,
even if they're tedious.
right. But a problem, on the other hand,
Well,
well, that's a different beast altogether.
okay, so what makes something a problem then, in his view?
Well, according to Zeitz, a problem is something you can't answer immediately. It often feels open-ended, maybe even a paradoxical. It requires real investigation, poking around, trying things, before you even get close to figuring it out.
And this kind of problem solving, it's not just some abstract academic thing, is it?
Oh, absolutely not. Zeitz makes the point that research mathematicians, well, they live and breathe this kind of open-ended problem solving.
Uh-huh.
And think about the real world, right? In almost any industry, being able to tackle poorly defined problems, messy problems, is way more valuable than just knowing how to run a standard procedure.
Yeah, a computer can follow instructions perfectly. It can invert a matrix faster than any human,
Exactly.
but it can't figure out how to approach something completely novel it's never been programmed for.
So, like in everyday life, maybe fixing a weird noise your car is making without a clear guide, that's more of a problem. Whereas following a detailed recipe is more like an exercise.
That's a fantastic way to put it. Exactly. The problem demands diagnosis, hypothesis, testing. The exercise gives you the roadmap.
Okay, so for you, the listener, our mission today is pretty clear, I think. We want to pull out the core strategies, the key insights from Zeitz's work to give you a better toolkit for approaching all kinds of problems, not just math ones.
Yeah, the goal is to help you move beyond just that rote exercise solving mode and really embrace the art of investigation.
Okay, so where do we even begin? You're faced with this thing that seems impossible. Zeitz actually starts with the importance of mindset, the psychological side of things.
Right, the strategy's inside your head before you even start scribbling.
Yeah. He basically says effective problem solvers just think differently. They're tougher, mentally tougher, more sensitive to patterns maybe, and definitely more flexible.
And the really hopeful part is he argues these aren't just traits you're born with. They can be learned, developed.
Like building a muscle.
Exactly.
Hmm.
And that connects to his idea about gradually increasing your intellectual load, right?
Yeah, tell us about that.
Well, it's like physical training. You wouldn't try to lift 300 pounds on your first day at the gym. You start with easier problems, things you can solve to build confidence, get warmed up.
Okay.
And then you progressively tackle harder ones, things that really stretch you.
It's about building up that frustration threshold, he calls it.
Yeah, that's key.
Initially, maybe you feel totally drained after just, I don't know, 15 minutes of really hard thinking.
Common feeling.
But with practice, you find you can focus for longer, an hour, maybe more. And he also talks about letting problems just kind of simmer.
Ah, the back burner idea.
Yeah, put it aside for days, weeks even. Let your subconscious chew on it. Sometimes the breakthrough comes when you're not actively hammering away at it.
That ties into something he mentions later, too, this idea of peripheral vision. Sometimes you're staring so hard at the obvious path.
That you miss something on the edge.
Exactly. You need to step back, look at the whole picture, notice connections or patterns that aren't immediately apparent.
Which actually brings us right back to that puzzle I started with. OTTFFSE.
Okay, so the answer.
The answer is N for 9.
Ah, 1, 2, 3, 4, 5, 6, 7, 8, 9. The first letters. Okay.
Right. It's not calculation. It's pure pattern recognition, but not a mathematical pattern in the usual sense. It's a perfect little example of needing that different way of looking.
That's clever. Zeitz has another one like that, doesn't he? With a table of numbers.
Well, yeah, the grid looks totally random if you go row by row, right?
Utterly baffling.
But if you just kind of relax your eyes, scan the whole thing.
You start seeing familiar numbers pop out. Like multiples of 3, wasn't it?
Exactly. Multiples of 3 hidden diagonally or in other weird patterns within the grid. It's a great reminder to look beyond the immediate structure you're given.
Okay, so mindset is key.
Mm.
Resilience, flexibility, peripheral vision. Now, what about actually doing something? What tools does Zeitz offer?
Right, now we get practical. He introduces this thing called the affirmative action problem. It involves a network of colored balls, like marbles, say white and black, connected by wires or strings.
Okay, a network graph kind of thing.
Yeah, and the problem defines a state where each white marble has at least as many black neighbors as white neighbors, and vice versa for the black marbles. The puzzle is about colorings of these networks that satisfy this condition.
Sounds potentially complicated. What's the point he's making with this one?
It's about the imaginative leap needed for the solution. He puts it under psychological strategies because the elegant solution involves reframing what integrated means in this context in a really non-obvious way.
Ah, so it's about breaking free from your initial assumptions about what the problem is asking.
Precisely. It shows how that kind of flexibility can lead to surprisingly simple answers sometimes. He connects this ability to things like solving ciphers or crosswords stimulating association, deduction, concentration.
Though maybe don't get too hooked on the crosswords.
Yeah, he adds that little caveat. He also throws in a couple of other deceptively simple ones. There's the classic bottle A, bottle B thing.
Oh, the milk and coffee one.
That's the one. Pour some milk into the coffee, mix it up, pour the same amount back into the milk bottle. Both bottles end up with the same total volume.
And the question is there more coffee in the milk bottle or more milk in the coffee bottle?
Right. Your intuition might lean one way, but the actual relationship between the fractions is, well, quite elegant and maybe surprising.
Yeah, it forces you to think carefully about what's actually being exchanged. And then there's the Indiana Jones one.
Oh, the rope bridge. A fantastic logistical puzzle.
Love that one.
You've got Indy, his girlfriend, his dad, and the sidekick. They need to cross this rickety bridge over a gorge.
At night.
At night, with only one flashlight. And the bridge only holds 2 people max.
And they have to travel at the speed of the slower person.
And there's a time limit, 1 hour, I think.
Yeah, something tight like that.
Yeah.
It's brilliant because it forces you to think purely about constraints, trade-offs, efficiency. How do you optimize moving people and the flashlight back and forth?
It's a perfect example of how just clearly understanding the rules, the limitations, can really guide your investigation.
Okay, so you've got your head screwed on,
Yeah.
right? You're ready to be flexible, persistent. What are some actual concrete strategies Zeitz suggests for starting the investigation?
Okay, yeah, moving from the psychological prac to the practical tools, he offers some really useful techniques here.
Like the penultimate step.
Exactly, that's one of the first big ones. Once you know where you want to end up, the conclusion you need to prove, you ask yourself, what single step right before the end would get me there?
So you're working backwards from the finish line.
Precisely. Instead of getting lost in the messy start, you envision the final connection. It's really helpful when the path forward looks totally unclear.
Can you give an example?
Sure, like if you need to prove 2 complicated things, A and B are actually equal. A penultimate step might be to prove, separately, that A is greater than or equal to B, and that B is greater than or equal to A.
Okay.
Yeah.
If neither can be bigger than the other, they must be equal. Makes sense.
Or if you want to prove A is not equal to B, maybe you show A always has some property, like it's always even, and B always has a different property, like it's always odd.
Yeah.
Then they can't be equal.
Right. And Zeitz says that experience helps you spot these potential penultimate steps more easily. Yeah.
Definitely. And the more problems you see, the more these patterns emerge.
What else? There was something about wishful thinking.
Yes, wishful thinking and make it easier. This is a great, like kind of blending psychology and math.
How did that work?
The idea is figure out what makes the problem hard. Is it ugly numbers, complicated algebra, a weird constraint?
Okay.
And then Just temporarily wish it away, make the difficulty vanish for a moment.
Like pretend the numbers are simple. Or ignore that tricky constraint.
Exactly. Ask, what if this hard part wasn't here? By tackling an easier version, you can often get traction, understand the core structure, and gain insights that help with the original harder problem.
Hmm, I could see that. Like getting a feel for the landscape on easier terrain before tackling the mountain.
Right. He mentions an example with infinite geometric series. You might guess the sum by looking at the pattern the first few terms, essentially wishing away the infinite part just to get a plausible answer to test.
And even if that simplified version doesn't give the final answer, Zeitz argues it can help you zero in on the real difficulty.
Right. Yeah, it might force you to ask a better intermediate question. And honestly, just making some progress, even on a simplified version, can really boost your confidence, makes the whole thing less intimidating.
Okay, that makes a lot of sense. So you investigate, you try things,
Yeah.
but then you need to convince someone or yourself that you're right.
Ah, yes. The second crucial part. Zeitz really emphasizes this. Problem solving has two sides. There's the investigation, the messy, creative discovery part.
Right, the figuring it out.
And then there's the argument, the clean, logical, convincing part where you lay out your reasoning.
And often the way you investigated the patterns you found, they kind of suggest how you might build that argument, don't they?
For sure, your exploration can point towards the proof. And speaking of proofs and arguments, Zeitz touches on the importance of clear communication in math.
Yeah, laying things out properly.
He mentions that good arguments usually start with really clear statements. Here's my hypothesis, what I'm assuming, and here's my conclusion, what I'm trying to prove.
Getting the setup right. He also talks about notation, like marking the end of a proof.
Yeah, the little filled square, the HOMO symbol, or the classic QED, or even things like AWD for and we're done, or W5 for which was what we wanted, little signposts.
Keeps things clear.
Yeah,
And he stresses using proper sentences, right? Not
Yeah.
just strings of symbols.
absolutely. Complete sentences with nouns and verbs, just like any good writing. And he introduces that useful notation, colon equals.
Where meaning is defined to be.
Right, emphasizing that you're defining something new on the left in terms of stuff you already know on the right.
Okay, so how do we actually build an argument? Does he give examples of proof techniques?
Oh, yeah. He walks through a great example to illustrate argument construction, proving that the equation x squared plus x plus 1 equals y squared has no positive integer solutions.
Okay.
How's that done?
He uses proof by contradiction. It's a really powerful technique.
Where you assume the opposite of what you want to prove.
Exactly. You assume there are positive integers x and y that satisfy the equation. Then you manipulate it, in this case by factoring, and show that this assumption leads to a logical impossibility, a contradiction.
So if the opposite leads to nonsense, the original statement must be true. Clever.
Very. He formalizes contradiction again with a number theory example, showing that if p is a prime number and x isn't a multiple of p, then the numbers x, 2x, 3x, all the way up to p1x are all distinct when you look at their remainders after dividing by p, what we call modulo p. So none of them leave the same remainder when you divide by p.
Right. And again, the proof works by assuming two of them do have the same remainder, the opposite, and then showing this leads to a contradiction with the fact that p is prime and doesn't divide x.
Okay, contradiction is powerful. What else? Induction.
Yes, the principle of mathematical induction. Crucial for proving statements about integers, usually statements that hold for all integers starting from some point.
The domino analogy comes to mind.
That's the classic one he uses. You need to show two things. First, that the first domino falls. That's the base case, proving the statement for the starting integer, often NA1 or N0.
Okay, knock over the first one.
And second, you need to show that if any one domino falls, say the kth domino, then it necessarily knocks over the next one, the k plus 1th domino. That's the inductive step.
So if k is true, then k plus 1 must also be true.
Right. If you prove both the base case and the inductive step, then it's like a chain reaction. All the dominoes must fall. All the integers satisfy the statement.
And sometimes the tricky part is figuring out how to set up that inductive step, right? Choosing the right in.
Exactly. He emphasizes that choosing the right index the in you're inducting on is sometimes the key. And finding a clever way to relate the problem for n plus 1 back to the assumed truth for n.
Does he have an example for that?
Yeah, he uses one about coloring regions formed by lines drawn in a plane. If you draw a bunch of lines, they divide the plane into regions. The problem is to show you can always color these regions with just two colors so that no two adjacent regions share the same color.
Like a map coloring problem, but simpler.
Kinda. And the key to the induction proof is realizing that if you have a valid two coloring for n lines, when you add the n plus 1th line, you can cleverly adjust the coloring on one side of the new line to maintain the two color property. The number of lines becomes the natural index n.
Okay, so the structure of adding one more line lets you build the proof inductively. That makes sense.
This whole idea of changing how you look at things, it's a recurring theme, isn't it?
Hugely powerful. Zeitz actually dedicates a specific section to this strategy. Pictures don't help. Recast the problem in other ways.
Right. Visualizing can be great, but sometimes you get stuck in one way of seeing it.
Exactly. He argues you need to be ready to completely reinterpret the problem.
He brings back that earlier example, the sequence of numbers that turn out to be descriptions of numbers. Remember O, T, T, F?
Yeah, the 1, 2, 3 thing. A playful example of how the problem might not be what you initially assume it is.
And he mentions the locker problem, too. Starts as a combinatorial question. You know, kids opening and closing lockers in sequence.
Which lockers end up open.
But the solution involves number theory. It turns into a question about how many divisors a number has. It's a great example of crossover between different math fields.
Showing how these areas aren't really separate boxes. They connect.
And then he mentions the ultimate example of reformulation, maybe in all of math history.
It has to be Descartes, right?
Yep. René Descartes, recasting geometry problems into the language of algebra.
Analytic geometry, which basically paved the way for calculus.
A total revolution in thinking just by changing the representation. It's incredible.
Zeitz has a really neat little puzzle to drive this home too, doesn't he? The swimmer and the hat.
Oh, that's a clever one. A swimmer's in a river, throws their hat upstream, or maybe just lets it float downstream. Wait, how does it go?
I think they start swimming downstream, the hat falls off or they throw it, and floats downstream too. The swimmer continues downstream for, say, an hour.
Okay, downstream for an hour.
Then they realize, turn around, and swim back upstream at the same speed relative to the water to get the hat.
And the question is just, how long does it take them to get back to the hat after they turn around?
Right. And you could set up equations with the swimmer speed, the current speed, distances. It gets messy.
Yeah, my head hurts thinking about that.
But the elegant solution comes from a complete change of perspective. Think about it from the hat's point of view.
Okay.
The hat is just floating.
Right. It's stationary relative to the water. The swimmer swims away from it for 1 hour.
And then swims back towards it at the same speed relative to the water. So how long does it take to return?
It must take 1 hour because the current affects them both equally relative to each other. Wow.
Exactly. Changing the frame of reference makes it almost trivial. That's the power of reinterpretation.
Okay, that's brilliant. So after covering all these mindsets and strategies, Zeitz kind of wraps things up.
Yeah, he offers a sort of concise list, a reminder of the core problem-solving ideas we've encountered throughout the book.
Like what? Just rattle off a few.
Okay, experimentation, definitely. Looking for patterns, making conjectures, testing them, using counterexample.
Breaking problems down, working backwards.
Considering extreme cases, exploiting symmetry, looking for things that don't change, invariants.
Using tools like modular arithmetic, the pigeonhole principle.
And of course, that big one, reinterpretation, recasting the problem.
Wow. Okay, so let's try to summarize our deep dive today. What are the big takeaways?
Well, I think the main thing is that problem solving isn't some mystical talent. It's a skill, a craft. Like the title says, it can be learned and developed.
Right. And it involves more than just knowing formulas. It starts with understanding the difference between a routine exercise and a genuine problem.
They're adopting those psychological strategies, building resilience, being flexible, being okay with getting stuck for a bit.
And then having a toolkit of investigation techniques, working backwards, simplifying, looking for patterns, all that stuff we discussed.
Plus, learning how to actually structure and communicate a clear, logical argument once you think you found something.
And maybe underpinning all of it is that willingness to reinterpret, to look at things from different angles.
Definitely. Leveraging those fundamental ideas across different contexts.
So for you, the listener, hopefully this deep dive has given you a richer toolkit, some new perspectives.
Yeah, and remember, these aren't just for math Olympiads, you know. This kind of thinking applies everywhere. Work, personal projects, figuring out confusing instructions.
Anywhere you face something that doesn't have an easy, obvious answer. It's about moving beyond just following steps and really engaging with the challenge.
Fostering those deeper analytical skills and hopefully gaining a bit more appreciation for the whole messy, frustrating but ultimately rewarding process of solving problems.
Well said. And maybe on that note, here's a final little thought for you to chew on. Think about a time you were really truly stuck on some problem. Could be anything.
Hmm.
Looking back now, with some of these strategies in mind, wishful thinking, working backwards, changing perspective, what might you have tried differently?
That's a great question.
Because the art and craft of problem solving, as Zeitz lays it out so well, it really is a lifelong journey, isn't it? A journey of learning and discovery.